Well, hi, and welcome to my shop. Thank you so much for joining me here on August 4th for another day on this very interesting CB test equipment. It's getting more interesting the more I do with it. So just another warning, this is basically a live video. I have not, what you're seeing me do, I'm doing for the first time, so that means I can make mistakes and overlook things and the like. But nevertheless, I've managed to get to this point where I've individually checked each one of these pieces of equipment. They seem to be okay. I've messed around with a couple of radios. This guy not so good. This guy fairly, really, it's almost new out of the box radio. It's in good shape. And I've exercised having all the equipment connected together just to see kind of how you use it, if you cared to. And the last thing was a few deficiencies in the operation of this equipment I noticed. Over here was the percent distortion, the method for measuring the harmonic distortion percentage in the audio of a radio like this little one here. Probably a couple other things not quite working right. This thing reads various values on its meters, but are they reading correctly? Is this thing calibrated? That's really the question. I've read over the calibration instructions that are in the service manual. It's not too difficult. So I think what I want to do today is run through the calibration processes for this machine, try to calibrate this in accordance with those instructions, and maybe have a little better operation of it. Maybe bring this function over here, the distortion function, make it operate properly. I may also discover defective components in here. It's quite possible. And I don't even really know what's, well, I do know what's in here. I've been looking at the service manual. So next we are going to look at the service manual. I'm going to run through it very quickly just to see what it's all about. And then I'm going to read through the calibration procedures. And then we're going to get busy on here. So let's jump over and take a look at the manual here. There it is, the 1040 CB Service Master. It's a bad photograph of it. Read the description here. Oops. The Model 1040 CB Service Master is a high-quality test instrument designed to primarily test Class D Citizens Band transceivers in the 27 MHz band. It will also test other types of bands of two-way radio transceivers, transmitters, receivers, and audio equipment. The Model 1040 is capable of checking receiver sensitivity, audio output power, audio distortion, transmitter frequency, modulation, PF, I think that should be RF power output, and antenna standing wave ratio for both AM and single sideband operation. The Model 1040 is a rugged, lightweight, reliable instrument. It is completely solid state, providing instant warm-up time and low power drain. The unit operates from 120 volts 60 Hz or for bench servicing, or from a 12 volt power source for convenience in vehicle testing. So there was a hint in there. It says it's completely solid state. So that puts this thing back into the early 70s, because by the 80s nobody would make that statement, because everything was completely solid state. This might be older than I realize. Might come from the mid 1970s or maybe even a little bit earlier. Okay, so a bunch of specifications. Here, how to take it apart. This part here, remove the bottom cover. This is all I need to do. I'm not taking boards out of it or anything like that. I don't expect to be doing that. Reassembly, just do everything the other way around. Here we are, calibrations and adjustments. Let's not read them yet. Let's just look down through the whole manual. So here's the different adjustments that can be made. I believe these are all variable resistors, capacitors, other things. This diagram is very important during the adjustment points. Here's a troubleshooting chart. This is pretty sad. Troubleshooting chart. some parts location diagrams showing you where certain parts are. The layout of the circuit boards. It does talk somewhere about it using the newfangled circuit boards. So once again, that throws it back. Ooh, that throws it back to the early 70s. Circuit boards, newfangled. Somewhere in there, I thought I read that. Part layout. Look at these big resistors here. These are the same board, different parts, capacitors. Now, lots of parts in this thing. Looking at the underside of the circuit boards, showing you the different terminals on all the transistors that are in here. And a chart of voltage measurements, which might prove to be very, very useful. Done with a VTVM or equivalent. So notice here they're saying a VTVM, vacuum tube voltmeter. So again, this is pointing to the early 70s, in fact, that this may have been made. Maybe it might be a little older than I thought. So we're going to go up to the calibration. I'm going to read through these quickly. Model 1040 has been precisely calibrated at the factory for optimum performance and should not require readjustment unless a defective component has been replaced and it is absolutely certain that the unit will need to be calibrated. Well, when you go this far down the road, so many years have gone by, I think, and with the indications we've gotten, I think going through the calibration process is worthwhile at this point, even if I don't change a part. Remove a couple of screws. Here's what we need. We need a watt meter. We need a now watt meter. Do I have a watt meter that I can rely on? Probably do, actually. Watt meter, frequency counter, oscilloscope, audio generator, AC voltmeter, audio amplifier. What do you need an audio amplifier for? Procedure: RF watt meter calibration. Connect the RF output. So I've read through this and I can tell you it's really simple. Hook up a watt meter in series with the one that's built into it and see what the one you've hooked up says, and adjust the one that's built in to match the one you hooked up, because you hooked up a valid one. That's what that really says. 26 megahertz oscillator adjustment. Now 26 megahertz. What's this all about? The actual frequency is 26.255. So they're using this frequency to mix with the output of the radio you're testing to produce a 1 megahertz difference frequency, which it then produces that frequency at a terminal you hook up to your oscilloscope. So while your radio is transmitting 27 megahertz, this thing's converting it to 1, so you can put a lousy cheap oscilloscope on it and see it. An oscilloscope that maybe only goes to 5 megahertz or something like that. 5 or 10 megahertz. Doesn't go all the way up to 30. So you cannot see the output directly. That's a pretty attractive feature. Back in the day, it's a pretty attractive feature. Two-tone amplifier adjustment. Okay, so we don't have to read, but this involves a lot of reading of voltages on certain transistors. We'll see about doing that. Remove capacitor from Q7. So even putting in temporary components to create a circuit that will provide some way to make this adjustment. A temporary circuit. Audio watt meter. There's a voltage reading here somewhere you take right here. And the different resistances like 8 ohms, 4 ohms, and 16 ohms. You get different voltages you're targeting here. Boop, that's the end of it. That was the end of it. Okay, so just very quickly now. RF watt meter calibration. 26 megahertz oscillator adjustment. Two-tone amplifier adjustment. Audio watt meter calibration. That's it. Those are the items. Well, we're bound to start off with this. Okay, let's take a look inside this machine now and see what it looks like. Okay, 5 screws to remove. Disconnect these. Okay, power's off to everything. Let's see. 5 screws. 1, 2, 3, 4, 5. Okay. Somewhere in the manual it says all the calibration can be done by just removing this back panel and nothing more. Had another tornado warning. Well, I don't know, we actually got a tornado warning last night. Heavy thunderstorms. Not so bad here. We didn't get hail or anything, but I think there was another tornado in Ottawa. Ottawa's quite a distance from here. It's, 300 kilometers or so. Certainly no shortage of rain this year. There we go. This just comes out nicely like that. Wow, that's a lot more in it there than I expected. Much more to this. Right, now I guess we can put it down this way. Okay, let's take a good look at this. So first of all, is there anything leaping out here? Sticker here. I think that says 76. I think it says 10. Could be 10, 15, 76. And then initials. Looks like 3 sets of initials on here, perhaps. Okay, we got a fuse hidden away inside. Because there's a fuse on the back of this, is there not? There is not. There's not a fuse on the back, so there's one hidden inside. You have 2 diodes here. They're not identical. That's a little odd. Maybe they are identical. Oh, here's another one out here. Okay, I'm just looking for any odd signs. Somebody's been in here, work has been done, things have been changed. Stuff is getting hot. I'm looking for solder. Everything looks perfectly fine. I see nothing here at all. But I also don't see, where's the, so here's a couple of adjustments hidden here. 1, 2, 3, 4. They look like adjustments. More here. There's a bunch under here. Hard to spot. 1, 2, 3. Okay. So I think we're good to go here. I have it upside down now, so I can't see the front panel. So I guess some of this, I'll have to have this on its side to do some of this work so we can see the front panel while making the adjustment. Very good. Okay, I think it's coffee break time here before I get going on this. Fantastic. I was busily hooking up these 2 meters here, Micronta field strength SWR tester meters, thinking they were watt meters, when I suddenly realized, no, these guys won't measure watts. The best they'll do is show you the percentage of your calibration setting, which doesn't mean anything at all. It's just, so can't use these, but I do have another, I do have I have another watt meter. I have to disconnect it from where it is. It's an older one too, and I don't know. But it's what I got, so I'm going to go get it. Goodbye to these ones. Okay, we're going to try this Micronta 3-way CB tester. So it has a standing wave ratio and modulation with 2 calibration adjustments for those, and then RF power just straight up, no calibration, direct reading. I have my own dummy load here. See, there's a resistor in the back of that. Let's just see what the resistance is. It's supposed to be 50 ohms. Let's find out. Wow, 50.3. Okay, that's plenty close. Good. Okay, and that can probably take, I don't know, 10 watts for a minute, maybe not quite so much, but no 10 watts coming out of this. So we have a known resistor here we can use. There's a built-in one right in here, and I've got it switched to the built-in setting. I'm going to put the power on. Okay, everything came on here. I think I'm just going to turn the scope off because we're ignoring that for now. And this guy has vacuum tubes in him, so the less we turn it on unnecessarily, the better. Okay, so I have this radio. Now the problem here with this radio is it's hooked up to a lousy power supply, and I believe the supply voltage is coming down when you hit transmit. We are only talking about a few watts here. It's not a lot going on, but okay, we're all set. I think we're set to go. So we're on channel 10, dummy load. This cable, this big cable here, which is going to this guy, is coming from the antenna output. The antenna input's going over to the transmitter or transceiver. Here we go. Let's watch this meter first. Forward power 10. With the meter on its side, by the way, the meter has an easier time going upscale. Okay, so this guy is reading about 2.8. That's what I would say. He just said it was 2.8. Now, what's this one say? If it's 2.8, don't fall over now. Oh, it's bumping into big cables here. There we are. So 2.8 is 1, 2, you can just see it. So this one's reading 3.8. Oh, that's a nicer number. That's close to 4. Isn't that what it's supposed to be? 4 watts? I don't even know what the output is supposed to be. This is not dimming much. That's a good sign. Okay, we're going to switch to this alternate one and see what the difference is. So I'm going to put this into the external load connection, flip it over. Okay, any different? First of all, I will tell you what this watt meter reads here. It reads 1.4 watts. And what's this one read? 2, just above 2. Now I'm going to flip the internal switch here. Did you see that jump way up? And the other one does the same thing? Yes, the other one's doing the same thing. Why? Why would that be? Why would that be? That's what the internal load. So that's showing almost 4 watts. But we flip to the external load, and we're a little over 2. So these kinds of things just make me think, wow, this is all kind of a joke in a way, isn't it? I shouldn't think that, but I started thinking stuff like that. Well, let's look at the reverse power from these two different settings. So first, internal reverse power. We can't really do it with this meter, but the other one on the machine promises to do it. So let's take a look. What do you say here? So we're on reverse power. The meter just barely moving here. And we'll go on the external load. Look at that. Well, that would explain the difference then in the reading of how much power is going out. Because I believe it's power out minus power coming back, and you get your reading. I think that's how these would work. Maybe not this one. This one has a forward setting and a reverse setting. So you think in the forward setting we see everything. That's really weak. 1.5 here. In the reverse setting we see even more. Oh my gosh. Both the internal load, forward power, just about, I tend to read the wrong scale here, 2.5 watts on here, almost 4 on the other meter. And reverse, almost no reverse. Well, what's happening just from making this little change here? Making a huge difference. Yeah, that's why theory's great. Doesn't work. Well, let's try measuring the standing wave ratio, which I'm not really sure what it means when you're feeding right into a a perfect load that's located so close to the transmitter. So close to the transmitter. Okay, here we go. First we do the setting. And now we say, what do you think the SWR is into the internal load? The SWR is like 1.1 to 1. I mean, it's right down there. We flip to the external load. Oh my gosh, what is happening? It's as if there's nothing there. But I measured this. There's definitely 50 ohms there. What's the action here? How does this happen? With the proper load. Run SWR. Let's go reverse power. Supposedly 1 watt coming back in reverse. But on the internal, next to nothing. Take this off. Everything should come back, shouldn't it? Just over 1. Just over 1. That's to the open, to an open connector. I'm not sure I'm doing anything sensible here. Transmitting into an open connector. That's the SWR. Woo! Right off the scale. That's what you would expect, isn't it? Put this guy in. Set. Well, even with this in, something going on there. Something's not quite right, I would say. Now I have had this in another circumstance in my house, hooked up to an antenna here, my 102-inch whip antenna outside. And I was picking stuff up, coming in through here, out through here, and up to the radio. It was receiving. There is some kind of connection through here. I don't know what to make of that. Move the watt meter from where it is on the input side. We can move it to the output side here, because right now the radio's output's going through this meter and then down into here. I can move the meter, the watt meter, so it's here. We can see what's coming out. Let's try that. Let's try that. So, you know, I think always when you're doing this kind of stuff, you get unexpected results, partially because, you know, I'm new to this stuff, so it could be things I don't understand yet. As simple as this all seems to me, what do we want to do? We want to feed the transmitter straight into the Service Master. I wonder how long it took them to come up with that name, Service Master. Do I have an angle? I have an angle thing here, right here. Where's the angle thing? Here it is. Think these angle things would make a difference? I don't think so. Okay, this is the output from the transmitter. In here. And now we want the output from here on this long cable. Makes a difference, I think. I want this to come up here. And we want this to be over here. And we want to put the dummy load out here. The 50 ohm resistor. There we go. RF power. Okay, so this is set to forward, and this is set to internal to start. And here we go, channel 10. Okay, so we're reading on here about 2.2 watts. Seems like a little more. We'll flip this. So we're now coming out into this meter. And that's reading just under 2 watts here into this dummy load. This one's reading again 1.1, and this one's reading just under 2 watts. Uh-oh, it's the 2 watch problem again. You know, the man with 2 watches never knows what time it is. So, which meter is accurate? I've got some experience of this one, and it's quite believable usually, but that's not proof of anything. I think if we want to prove something here, we have to get a voltmeter that we can trust and read the voltage that's developing across the dummy load. And that's tricky business. It's 27 megahertz. I could do it on a scope. I have scopes that'll go that high. Pretty sure. I also have voltmeters. You know, it's an AC signal. I have voltmeters that would do this kind of thing with DC, but on the AC side, I'm not so sure. Well, I think we should try the scope. Scope is probably the least risky. Risky? Is there a risk? Is there some risk here? Risk of embarrassment running really high, that's for sure. So I'm going to run and have some coffee. Okay, here's what I've got. Just this piece and this radio are connected. The rest of this equipment is not doing anything. You see the oscilloscope in the back. The output from the radio is coming down here to a T. The T is hooked up to the oscilloscope and continues on also. Yeah, this way, Jim. Into the device, and then back out, if we care, on this big cable here, up onto this guy with a dummy load in behind. So I'm just able to basically measure the output voltage of the transmitter on my scope. So I think. Let's see what we get. Good. Okay, I'm going to just brighten this up. You can see it there. So I'm on the I'm on the times 10, I believe. That's no times 10 difference. Really, watch the, sorry about all these wires, watch the watt meter here as I flip the scope probe from from 1 to 10. So I guess basically it's a million ohms versus 10 million ohms. Kind of think of it that way, I think. Load being put on here, it's nothing. It should be nothing. Here we go. Okay, watching that watt meter. You see it moving? I don't get it. Whoops. Cast my eyes up here. I haven't been watching this one. Let's watch this one. Hey, why is it not going? Oh yeah, because I don't have it this way. Let's flip it this way. Try the same things. So, okay, I'm going to flip the thing here. Same effect. A little loose. Who's loose? What's with the jumps here? Bad connector. Maybe I've got a bad connector here. Oh, that's not going to help out at all. How could that be bad? There's nothing to it. Let's try this one. These banana connectors go right into the PL259s very nicely. This is loose. So I can't tighten this right up. This is probably the problem here. There's interference with the, so still a little bit of looseness in there. That might be what's really happening. Put this on the scope. Okay, everybody hang in there. There we go. Still jumpy. Can't quite see what I'm up to. I'm just swinging this. That's the times 1 and that's the times 10. Who's causing the wonkiness here? Can't believe it's my scope lead. That's hard to believe. Let's try another one. Uh-oh, this is a brand new one. Well, brand new old one. No 10 on it. Seems to be working. So not the best idea to use something you're not familiar with. Transmit. Oh my gosh. Going right off the scale, I think. Ooh, I can't believe that. My other test lead's not working. Oh, I think we're good to go now. Jeepers. The snapping is a relay inside here. Looks stable. Let's get some readings now. Okay, so we're going to go internal. This guy reads 1.5, just about exactly. And this guy reads, well, we can't do it on internal. He's not going to read anything. Back on external. Okay. Now we're reading 1.3. 1.3, and up here, that's 1.9 or 1.8. In all cases, this is always reading low, and I've had the impression that it's reading low. Okay, now we're going to try to measure the voltage here. This is the voltage right on the cable coming from the radio. We'll go back to the internal load for. I want to look at the. Yeah, I don't know what an SDR meter is really telling you when you have it terminated in a resistor right there. I don't know. There's no cable involved or anything. So we'll go to the internal one, and we'll read this voltage. So we're on the 5 volts per division scale here. And we're going 1, 2, 3, 4. Let me just 1, 2, 3, 4, 4.5 divisions. Okay, I'm going to stop and calculate. Okay, here's my fancy calculations, including the initial mistake. So at first I forgot it was peak to peak. I just went ahead and calculated it using peak to peak voltage here. Then you got this crazy number, 10 watts, what am I doing? Yeah, so then I converted the peak to RMS. So about 8 volts coming out RMS, coming out of the transmitter. So 8 volts squared, a little less than 8 volts squared, 61 divided by the resistance, and you get 1.2 watts. 1.2 watts. It's 1.2 watts. So we're on internal. Let me make a reading. This comes up to like about 1.7 or so. And this one's not on, so we'll flip it back this way. Do it again. Now it's about 1.3 watts, but this one is saying 1.8, and the calculation is 1.2. What about the voltage over here? Let me just flip this. Wow, you might see that change. So what I'm doing now is I'm flipping between the internal load and the external load. Just turning up the brightness a little bit. So we're on internal load, external load. Why is it changing? Well, the resistors must not be exact. Now the one I measured in my own little load, pretty much exactly 50. So, I mean, it's not a big difference, but so you got to ask yourself now, are you going to use this equipment to try to measure with precision the output of these radios, or are you kind of checking to see if it's there or not? If it's there or not, then this is fine. If you're trying to get some kind of precision, like for instance, there may be a target value that you're trying to set something in this radio to match a certain target voltage or something like that in the calibration instructions. Why am I even saying that? I don't know. I'm losing track of everything. I think I got to stop and just think about my next move here. What we're discovering is that things aren't as precise as you might imagine. Of course, that's always the case with this stuff. I don't know where to adjust this. If anything, it's reading high, and I thought it was reading low. But this last experiment suggests it's reading high. I'm reading the voltage rate coming out of the radio. Right here. So how could this reading be wrong on the scope? So you know what we could do? We can do this. Take this out. Yeah, put the load right on there. Isn't there a song like that? Put the load right on me. That's how the song goes. We're gonna put the load. Well, he could sing this song. He could be singing, "Put the load right on me." Anybody have a clue what I'm talking about? Okay. What's the difference now? Kenneth, what's happening? What's the frequency? Here we go. Whoops. The down button turns the transmitter on. Yeah, this isn't really the right microphone. Radio Shack. This is a radio. What's a Radio Shack radio? Okay, there's our signal. We're on internal. I'm just going to flip it to external while it's transmitting. Oh! I rest my case. What case is that? So we are measuring on the input. We are measuring the actual output of the radio. So in that sense, it's quite valid. I'm not measuring things on the far side of all this equipment. I'm measuring it right from the radio. What do we try a different frequency? It can't possibly have any effect. So let's find out. So we'll put this up to, we'll go right to the top here, which is 40. 40. Like there's 40 people. That's why you need 40 channels. There isn't 40 people in Canada using CB radios. Well, maybe there is. Here we go. What do we get? We get, okay, reading this meter, we get 1.6. Now we'll just go up one more, and we've actually gone to the other end of the band, and we get 1.6. Same reading. That's good. There's an average in the peak here. I believe the average is what you would use with an AM radio like this. If you had single sideband, you might have some trouble doing that, so maybe you put it like that. Makes no difference on the reading. Like maybe there's just a capacitor involved to integrate something. I don't know. Well, it's another fine mess I've gotten myself into. What did the instructions itself say about doing this? So we want to know about calibrating this meter. How do they approach the calibration of that meter? I think they said hook up a known watt meter and make it match. That doesn't sound like the best advice anymore, does it really? Depends how you hook up that watt meter. And we even found that the load from the scope is enough to unbalance this, which is really weird. I don't get that at all. Maybe this test lead is terrible at 30 megahertz. So maybe the test lead itself is affecting it. That's quite possible. Because I just grabbed this test lead. This is a new one to me, new old one. Let me go back to, you know what I'm going to get? I'm going to get a real McCoy scope lead for that scope. Just a real McCoy. Tectronic scope lead. And a long wire. Okay, so this one has a shorting button, but it's not a, it's a automatically reduces the signal going to the scope by a factor of 10. And by doing that, it reduces the load it puts on by a factor of 10. I know what I could have done here. I could have done a couple more things. So let's try this. Could have done a couple more things with the other load. You probably couldn't see it, but when I attach this scope lead to the scope value shown here changes automatically. So we have a little more sensitivity now, sort of. Put this on 10. So I think it's so this is direct reading. 10. This is 10 per division. We actually had it on 5 before. Let's put it on 5. So we should see kind of the same thing. Whew, right off the scale there. We'll go to 10. So I'm getting a totally different reading now from this. Is that what's happened? So if we're on the 10, for division, and we're going 1, 2, 3, 4 divisions. So that's 10, that's 40. That's 40. Oh my gosh. Well, before it was 20. Now we're getting 40 over there. It could be because of the capacitive effect of the test lead I put on. Maybe crap. Maybe crap. Okay, let's check that out. Let me find what I do with that test lead. Oh, here it is. So what we're going to do is, without even hooking it up to the scope, we're going to put it on here, just hang it on here. First, we have nothing on here. Oh my gosh, what am I doing here? We have nothing on here. Can't see anything, of course. Nothing on the scope now. How am I going to tell this? By the meter reading. Okay, so the meter says 2. Wow, now it says just over 2 watts. Just over 2 watts. Okay, we're not gonna hook this up to anything. We're just gonna drop it to the floor. And we're gonna put this. So this is basically, I'm hooking up a capacitor. That's what I think I'm doing. So what we want to do is we want to transmit and then remove this, and watch as it's transmitting what happens to the meter here. You can come a little closer actually. It's all about that meter down there. Meter behind all these cables. Go over there. Okay. Right, so we transmit and I just pull this off while transmitting. See how much just the lead on here can do. There's more effects here we're dealing with than just... Okay, here we go. And pull it off. You saw it. So what is happening here is probably reflections of signals in these cables. I don't really know, to be honest with you. I've been doing this for a long time. The SWR and reflecting signals in cables and cable impedance, and transmission lines, all that stuff is in my head. But I give it all a grain of salt, and the reason is when I come to do these kinds of tests, it looks to me like there are so many little hidden factors while you're doing it. Now, yes, I'm reminded of what I was told by one of my professors, and I've said this on quite a few, when I was in college, quite a few of my videos I've made this statement. I'm going to tell you this little story, and we're going to end the video, because I don't know really what to do next exactly. So we're in a lab, all of us, about 30 students studying electronics. We're in a lab, got our heads down. The instructor's at the front, sitting at a desk, very much like a high school classroom, practically, in the school I went to, college I went to. I went to Ryerson in Toronto. So suddenly he says, without any warning, guys, you know what's wrong with these things? And we all look up, and he's holding a regular voltmeter in his hand, like a multimeter, just holding it up in the air. I don't even think he even looked up at us. I can't remember now. He's holding it up in the air. Because you know what's wrong with these things? And we're all looking at each other. I'm not really sure what to say. And he goes, the problem with these things is they always give you a reading. And nothing more was said. But I went away thinking about what he said. And I realized what he was saying. It's not really the instrument that's telling you what's going on. It's you who's figuring out what's going on, and the instrument's throwing hints your way. And sometimes those hints are misleading. No matter what you do, when you hook up the meter, you're going to get a reading. You better hook up more than one meter, and you better do things more than one way. So you can finally get into that state like the guy with 2 watches who never knows what time it is. And I have no idea what's going on here in my shop. Okay, I'm going to call it quits here. I'm going to ponder this a little more. Try to do something. I don't know what I'm going to do here. Yeah, I don't know. I don't know what to think. That's great. I love that. That's great. Love having a gap. Got to go fill the gap. Thanks a lot for watching today, and tomorrow I'm going to carry on with this. don't know where it's going. See ya.